So let me talk about scalars, vectors, matrices. You know what is a scalar. What is a scalar? A number. A number that can vary from point to point, and we call a scalar field. Temperature is a scalar. There is one temperature in every point, not 10 temperatures. Density, it's also scalar. Okay, you know that, so no point. Vectors. Vectors, it's a more complicated issue. You need to define a vector with more than one number. How many numbers we need to define a vector? 2 in 2 dimensions, in the 3D Euclidean space, we need 3, okay? So vectors, okay, vector is a number with the velocity of this football ball, which is taking the point, that's a vector. That's the vector of the velocity. Matrices, we know also, you know what matrices are. You know the matrix of stresses, for instance. You have worked with that, of strains, all these kind of things. So it's just a sort of collection of numbers which are ordered in a certain way. Okay? But then there are other things which are a little more complex, and all of them are called tensors. Okay, all of them are called tensors. So what is a tensor? Is an entity, an algebraic entity, in our case, always representative of a physical property, which needs a number of several numbers to be identified. If the number is 1, so 1 to 0, one entity, it's a scalar. If there are 3, it's a vector. If there are more than, we'll talk about that, okay? Look, we look at tensors as something which is independent of the system of coordinates. For instance, if I'm talking about one vector that goes from this corner of this wick to this point of this door, that's a vector. Imagine this vector, okay? Now imagine that I take this system of coordinates here. There will be some components of this vector. You can identify them. If I change the system of coordinates, the component of this vector will be different, but the vector is the same. We use this vector to identify a specific quantity that is the locus of the points, or that goes from one place to another place of the space. So that is the concept. Tensors in continuum mechanics we are considering that are always representing some quantities that do not vary as we change the system of reference. But another issue is how do we express these quantities. But the quantity itself doesn't vary when we change the system of coordinates. So in terms of that, we have a scalar, which is what we call 0 dimension. A vector has 1 dimension. Why? Because it can be represented with a vector, a set of 3 orders, 3 figures, okay? Which are the components, we call the components of this vector in a certain system of coordinates. A matrix. Well, matrix, you know that to define a matrix, we need more issues, and we used to represent that in forms of a number of vectors, which are columns, or a number of vectors, which are rows, okay? So the set of these 9 numbers in that case is a tensor that we call matrix, but more rigorously we should call a second order tensor. Why second order? Because here you have 1 dimension. Here, to represent that with the matrix, we have 2 dimensions, vertical and horizontal, okay? Then we can extend that. We can just also try with a block of figures like that, having 3 dimensions. This dimension, and this dimension. That would be how many figures are there? 3 times 3 times 3, 27, right? And that would be a 3D matrix, having columns, rows, and depth. And that it would be a 3rd order tensor. It would be more difficult to plot a 4th order tensor, because for that I should resort to something that our brain is not able to perceive, which is 4 dimensions, okay? But I can imagine them. 4 order tensors, 5th order tensors, 6th order tensors, etc. So that is the first approach. How to represent that? We look, in general, a scalar zero-dimension tensor is represented by a single letter, in general, small letter, right? When we deal with a vector, in books, we use the boldface letter, boldface, because in books, I mean, you need doing boldface, as the word says so. But sometimes, when we are writing on hand, then we use a letter but underline with one bar. One bar means one dimension. That is a vector. A number with an underbar is a vector, means a vector. Because in the blackboard we are not able to write I mean, boldface and differentiate them. Two-dimension second-order tensors, matrices so to speak, are represented by a black capital letter and two underbars in other cases, if otherwise. Three-order tensors are represented by a calligraphic black bold-faced letter or three underlines and so on. And with this double line representation, we will use fourth-order letters, which implies four underbars here. Okay? So that is the first issue. Okay. Then, let's talk about components of tensor. Components of tensor are always related to what is the system of coordinates or the basis in which we are going to work. So in general, we use in the three-dimensional space, we use what we call a Cartesian basis or orthonormal base, in which we take three vectors, E1, E2, E3. In general, we require that the modulus, the length of each vector is 1. That is what means here. The modulus is 1. And they are orthogonal to each other. E1 is orthogonal to E2, and that's orthogonal E3. And according to them, we define three systems of coordinates, x1, x2, x3. You already know that. You already have been told that. Huh? So these vectors are ordered in a specific way, which is use the corkscrew rule. So moving on the corkscrew from E1 to E2, we get E3, etc. Or the right-hand rule, the E1, E2 moves according to these fingers, and the third is the other one finger. There are several ways of that. That is what we call a basis. But of course, I can use a number of bases. This is one basis, but this is one too, and this is one, and that's one. There are a number of bases. I choose one. And as I choose one basis, I can talk about components of tensor in this basis, related to this basis. By the way, we use the over sign circumflex accent, this accent here, which is hat. This is a hat, that to use that this is normalized, that the norm is 1. And then there is a property that we'll use, is that if we multiply any of these AI times the scalar product of any of these, aj is 1. If I is equal to j, so if multiplied by itself, or 0, because the dot product, the scalar product of two vectors, if they are orthogonal, is 0, as you know. So 0 otherwise. So that is what we represent. I will go back to that with the Kronecker delta, which is a symbol that has two subindices, ij. So when I is equal to j, that symbol takes the value 1, and when I is equivalent to j, that symbol takes the value 0. So we can just conclude that these vectors, these bases, are orthogonal and of norm 1, of absolute value 1, saying that ai times aj is equal to delta ij. That's the way, that's the notation that we use. That's algebra notation. That is a way to say that we are dealing with an orthonormal basis, which is orthonormal basis, which is orthogonal and normalized, the norm 1. Okay? So, let's talk about vectors, the system of coordinates that we have used, and a certain vector b. And once we have the vector and the system of coordinates, we can talk about the components. What are the components? Well, the vector can be expressed as a combination, linear combination, of these two vectors. So this vector 1 times a factor v1, which is that value here, which is the component 1 of this vector, plus vector 2 times v2, v2 is the component 2 of this vector, plus the component 3 times v3 is the component 3 of this vector. So once we have identified these three components, then we can talk about the matrix of components. So we have to distinguish between the vector and the components of the vector. The vector, as I told you, is something which doesn't change even if we change the system of coordinates. The components of the vectors, v1, v2, v3, depend on the system of coordinates that we have chosen. But if the system remains constant, as we have the three components, if I know these three numbers, I just multiplying the first one times e1, obtaining that, and then a2 times v2, obtaining that, summing them up, and e3 plus v3. If I sum these three vectors, I obtain the original vector. So, if we keep constant the system of coordinates, the tensor itself, in that case as first order vector, can be identified by a matrix which is an array of three numbers ordered in a form of a matrix of just one column that we call the components of the vector, the matrix of components of the vector, or the vector of components of this vector. Okay? Third, that is very long to say, right? So why don't we use something that you already know, the summatory notation? Instead of writing these three expressions, I just write B as the sum for EI equal 1, 2, or 3 of PI times EI. That means that I give the value I here, B1, E1, and then plus I give the value U2 here, 2 here, B2, E2, 3 here, V3, E3, etc. Okay? So that is the expression of the tensor, which is independent, that is general, because of course if I change the basis, I would have also to change that in order to V being the same. That is the tensor notation, the full notation of a tensor. But I can also use, if I'm going to work all the time with the same basis, I can use the component matrix, okay, the matrix of components, and then say that the component I of this matrix is VI. VI stands for I equal 1, the component of E1 on E1, I equal 2, the component on E2, I equal 3, the component of E3. That is trivial. I mean, you are boring now. I'm sorry for that. You knew that. Let's go to more complex issues. So, in abstract, what I've done so far, I've chosen a basis. I'm looking for combination, linear combination of these bases, and through these linear combinations, I've defined vectors, order 1 tensors, okay? So why don't do that using, instead of combining simple vectors, like this, why don't use double vectors, groups of 2 vectors? So once I have this basis, I construct what is called a second order basis, which is now grouping, dyads are called, the different vectors of the basis in groups of 2. So one group, one dyad, is E1 and E1. They are considered one group. And this symbol here, that we use sometimes, which is a cross circle, like that, it's called also tensor product, we'll talk about that, that implies that these two guys makes one element of the new basis, which is more complex than this one. It's not just by order 1 basis, it is order 2 basis, because there are the bases are grouped in 2, in groups of 2, E1, 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 E2, E1, E3, E2, E1, so the order matters, it's not the same. E2, E2, E3, E2, E3, etc. How many of them are there? Of course, 9. So now it's a little more abstract because I cannot represent that in a figure, but now I can say that if I combine every of these dyads or groups of 2 elements of the basis by coefficients 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, etc., there are 9 coefficients that multiplying to that return me something which is what I call second order tensor. So a second-order tensor is a linear combination of second-order bases, which are made of grouping 2 by 2 of a certain vector basis. That's it. Yeah.
Is there no way to visualize that?
No, unless you are alienígena. So today it's not possible, I would say. So that is why abstraction is useful, right? We have to abstract from that. But that is why I have started with something that you can visualize, which is a vector, and now I've just extended that by abstraction to something which we cannot visualize, which is a second-order tensor. So again, we can collect these coefficients in groups, in 9 groups. The one that gets the coefficient starting by 1, the one that gets the coefficient starting by 2, and the one that gets the coefficient starting by 3. And what do I obtain? A matrix. So a matrix, the matrix of coefficients, represents that tensor for these, of course, for this tensor, second-order tensor basis. If I changed E1, E2, E3, I take that, I would obtain a second-order basis different, and the components will be different. But otherwise, if I know that and the components are known, I know the tensor just by doing these operations. And that is the matrix notation for that tensor. Okay? Which is different. That changes, they have to keep in mind that this changes as we change the vector, the basis. Okay, so now we do that, and we can also represent as a symmetry. Now it's a double symmetry, I and j, and you look that all indexes that are repeated here, I is here, I is here, j is here, j is here, are summed up. I just take I1, and then I take 2 and 3 for j, A2, I2, and I took 1, 2, 3 for j, I3, and I take 1, 2, 3, and that is the representation of that. That is the short representation using the summatory notation. And then the component ij is just the component in the row I and column j of this matrix. You already are familiar with that. So let's do more complex. Third-order tensor. Now by extension, what would be third-order tensor? Just grouping the elements of the basis on groups of 3 triads, and then how many of them we'll have. If you do that example, we have 3 times 3 times 3, 27. And then the linear combinations of these 3-order triads then will return 3-order tensors. And the representation of the coefficients could be done in a matrix which is 3-dimensional matrix. Okay? That would be, now I need some perspective, I'm not able to do that in 2 dimensions, but that would be the matrix of components of the third-order tensor. Okay? Okay. Now, we are engineers. Engineers are always characterized by something. They try to save as much in money, in material, in effort, in time. That's our goal. Do it better, cheaper, faster. Okay? So, look, we can represent this third-order tensor here. IJK, that's a summatory, that's too long. Why don't I just cancel this summatory? Knowing that since this I is repeated, it would be here placed I and all the possible values of 2, 1, 3, 1. So instead of putting the summatory, you just replace that by that, and sometimes we also will skip even this sign. If there is no sign, that means that this is the tensor product, so that also is also equivalent with that. We have these 3 elements of the basis grouped together. That means that they are a basis of a third-order tensorial basis. Okay? Well, and this takes us to something which is the Einstein notation. Einstein notation. Einstein, you know, the famous scientist that invented the theory of relativity and so on. He also was a guy that was trying to save time, and he says, why? Why, if I want to express the product, the symmetry of AIVI from 1 to 3, which is too long, which could be replaced as a full expression, could be replaced by the symmetry expression, why don't I just suppress the symmetry and express that. That meaning that since this I is repeated, that means that there is a symmetry here. So whenever an index repeats, the expression should be considered as having a symmetry there, which is happening here. I repeat, so that is the symmetry, and that is that expression. If I had an expression like that, which is IAJ times BJ, then what is repeating here? The index j is repeating, but the index I is not. That means that I have to replace that by a symmetry on j only. So that's I1 B1 plus I2 B2 plus I3 B3. Okay? So only the repeated index, sum. The other index remain, like here, I remain. So that allows us, in an expression like that, to distinguish between a mute index. What is a mute index? It's an index that repeats. So for instance, imagine that I replace in that expression, instead of j, I put k. Aik times bk. What will be the result? The same. Because k would vary from k1, 2, and 3, and the result here would be the same. So k, or j here, which is repeated, is called mute, because at the final expression, it doesn't appear. But what about I? I here appears here, because there is nothing that specifies what I am talking of. So I is called a talking index. Okay? So in expressions now, that's the index or repeated index notation that says that in a monomial like that, whenever I have a repeated index, that index is summed up as many times as the possible values the index can take. And that is called a mute index, but it can be replaced by any other letter, and it won't affect the result. But if in that monomial there is one index which is not repeated, that is called a talking index, because in the final expression it remains. Okay? That is the notation that we'll use. It's just a matter of getting used to. If you get used to that, anytime you see that, immediately you will consider that that is a symmetry in there, repeating the index I. We do exercises about that. Okay? The index notation, sum over all repeated index, there are mute and talking indices, and it's extended. Many times you see, what happens if we have a derivative of ui with respect to xi? That, in that monomial, I is also repeating, is an index in that expression. So that is represented as the sum of I equal 1 to 3 of derivative of ui with respect to xy. So it's, in fact, the full expansion of that is derivative of u1 with respect to x1 plus derivative of u2 with respect to x2 plus derivative of u3 with respect to x3. Why? Because I varies from 1 to 3, and here this index is repeating. And even more, that is also sometimes too long, and we repeat that in order to represent that, which means derivative. We sometimes will use u, which is the function, I, which is the component of the function, comma, this comma means derivative with respect to, and j, with respect the coordinate we differentiate with. Okay? So these are, you are getting used little by little with that. We'll do that, we'll practice that in class, but that is the notation that we're going to use in order to make it faster. Because we don't want to write a lot. You just want to express what that we are going to represent here, these three sum of derivative. So instead of that we do that, and even instead of that we use that. And also it can be extended to second derivatives and so on. You have that here. Okay? The number of talking indices indicates the order of the tensor result. Look at here. Here, what is the talking index here? 0. There is no talking index. What is the result of that? And a scalar. Okay? But here, I obtain a number, a final expression that depends on I. So that can be a certain component of a vector for I equal 1, or for I equal 2, for I equal 3. So that could be the expression of a certain component of a vector, order 1 tensor. And this one here, or you can extend that and obtain also expressions depending on 2 talking indices, and then that would be components of a second order tensor.